Hello everyone, welcome to Dreamers.
In this video, we are going to discuss the basic postulates of quantum mechanics. We'll discuss 5 postulates of quantum mechanics. First, we'll discuss postulate 1, state of a system. The state of a quantum system is fully described by a state vector in a complex vector space known as the Hilbert space. Here, we are considering the state of a quantum system with n degrees of freedom corresponding to n generalized coordinates. The state vector encodes all the information about the system. The state vector contains and serves as the basis to extract all the needed information about the system. Any superposition of state vectors is also state vectors. In some books, you may find that the state of a quantum system is fully described by a wave function given by psi rt. Wave function. Wave function. So, you may think, what is the basic difference between state vector and wave function? As already we have discussed that the state of a quantum system is fully described by state vector and the state of a quantum system is fully described by a wave function. Please note that the wave function and the state vector, the wave function and the state vector, the wave function and the state vector represent the same physical concept in quantum mechanics, the quantum state of a system. However, they are expressed differently depending on the formalism or notation being used. Wave function, we do use it in Schrodinger picture. In Schrodinger picture. In the Schrodinger picture, the wave function is the special representation of the quantum state. It depends explicitly on position r vector and time t. It is a function in the position representation. Please note that sometimes we will discuss about position representation or coordinate representation, as well as we will discuss momentum representation. So here in the position representation, where the state is expanded in terms of the position eigenbasis. So we can write psi r t is equal to r psi t. Please note that in Dirac notation, this is known as cat psi and this is known as bra psi, about which we will discuss later on. Now we are going to discuss about state vector. We do use state vector, as I have told you now, that in Dirac notation. The state vector is a more general and abstract representation of the quantum state in the Hilbert space. It does not explicitly depend on position. Instead, it is a vector that can be expressed in any basis. It can be expressed in any basis, such as position, momentum, energy. The wave function psi rt is a specific representation of the state vector in the position basis. So the wave function is the projection of the state vector onto the position eigenstate r vector. So we can write this is equal to r vector psi Now we will discuss the property of the wave function. Now we are going to discuss the properties of the wave function. For the wave function psi to be physically meaningful, it must satisfy the following property. That is, it must be continuous, finite, and single value. What is the meaning of continuous? The wave function must be smooth and without abrupt jumps or discontinuity. What is the meaning of finite? The wave function must remain finite at all points within the allowed domain of the coordinate. And the meaning of single value is that for a given set of coordinates and time, the wave function must yield a unique value. So please note that the wave function must be continuous, finite, and single valued. These conditions ensure that probability density mod psi square, which is used to calculate the probability of finding a particle in a specific region of space, remain well behaved and physically interpretable. Again, psi must be normalizable, which means psi must go to 0 as x, y, and z tends to plus minus infinity. In order that the integration of psi square over all space be a finite constant. And next important property is that we have already discussed psi must be continuous, single valued, and finite. And again, please note that the derivative of psi with respect to x, with respect to y, with respect to z, that is the derivative of wave function, must be continuous and single valued everywhere. Postulate 2. Observables and operators. In quantum mechanics, observable quantities like position, momentum, and energy are represented by operators. Each observable is associated with a Hermitian operator, ensuring that the measurement results are real number. If A is an observable, its corresponding operator is denoted as A cap. For example, position is represented by the operator x cap. Momentum is represented by the operator minus I square del by del x in one dimension. In three dimension, you can write P cap is equal to minus I h cross del. What is del? You can write del is equal to I del by del x plus j del by del y plus k del by del z. Please note that here I cap, j cap, k cap are unit vector, whereas this I is root over of minus 1. Postulate 3. Measurement and eigenvalue of an operator. When a measurement is made on a quantum system to observe a physical quantity that we say here observable, the only possible outcomes are the eigenvalue of the operator corresponding to that observable. If A cap is an operator and this A cap is an eigenstate of A cap with eigenvalue A, then you can write that A operates on A cap will give you eigenvalue A. This is known as eigenvalue, and this is known as eigenstate. The measurement will yield the value A with certainty if the system is in the state A cat. Postulate 4. Probabilistic outcome of measurement. If a quantum system is in a state psi cat and a measurement of an observable represented by operator A cap is made, the probability of obtaining a specific eigenvalue A associated with eigenstate A cat depends on the nature of the spectrum. Nature of the spectrum means whether the spectrum is discrete spectrum or continuous spectrum. So for discrete spectrum, the probability of obtaining the eigenvalue A is given by this formula, where this is the square modulus of the inner product between psi cat and the eigenstate A cat. For the continuous spectrum, the probability that a measurement yields a result in the interval A to A plus dA is given by this formula, where this quantity represents the probability density function for obtaining a value near A. Postulate 5. Time evolution of a system. The time evolution of the state of a quantum system is governed by the Schrödinger equation. If the system state at time t is represented by psi cat t, then the time evolution is described by the following formula. Okay, that is I square del psi by del t is equal to h psi t, where h cat is the Hamiltonian operator representing the total energy of the system. This equation indicates how the wave function changes over time. So we have discussed 5 postulates. The first 4 postulates describe the system. The first 4 postulates describe the system at a given time. The fifth shows how this description evolves in time. So in the next video we will solve some problems related to these postulates in order to have a better idea about the quantum mechanics. Thank you for your patience and kind attention.